Welcome to Programming in Modern C++. We are going to discuss module 58. In the last module, we have concluded discussions on smart pointers, their policies, and we have familiarized with resource management using standard smart pointers from the library. Specifically unique PTR, shared PTR and weak PTR, auto PTR is deprecated. In this module today, we are going to introduce the notion of concurrent programming in C++ using C++'s own thread support. So, for this you will need to have some understanding about concurrent programming, which I will assume that you have. If you do not, then you will have to read up other material to understand what is concurrent programming and what are its issues, because that is an area which is not limited to C++ programming. That is a general computer science knowledge about how do you program concurrently, parallelly and so on. Now, we will specifically expose here to the library support through std::thread component and bind component, and discuss what are some of the common bugs in thread programming that can happen, specifically the race condition and data race. And we will discuss examples of thread programs with such bugs and look at some of their solutions. So, this is the content for this module, and let us start discussing with thread programming in C++. You know about processes in systems, like process is when we start a program, it starts as a process and multiple processes run in the system at the same time, and the processes can exchange data by what is known as inter-process communication. So, processes can be concurrent, they can be parallel and so on. Now, thread is a lightweight process. A multiple threads run within one process. So, the advantage that threads have, that threads can communicate also through shared variables, shared data, because they are within one process space, which processes cannot do because they have to protect the boundary of the processes data from corruption from other processes and so on. But the threads, all threads are within one process and they can communicate to shared data. They can also do inter-process communication kind of mechanism, but they are necessarily lightweight processes. And therefore, in the recent past, recent in the sense of say last 2 decades, concurrent programming using threads have become a dominant feature. So, they naturally being in the address space of a single process, they share the address space with other threads and can communicate freely, and for decades the C programmers, C++ programmers have been doing concurrent programming, multi-threaded programming as it is said, using several different libraries, predominantly the POSIX library, which is common on the Linux platform, or say the Windows thread library. Then there are several others like Boost and so on and so forth. So, in that context, what is special about C++ 11 in the context of thread programming? The special thing is now C++ 11 onwards, the library, standard library itself provides complete support for multi-threaded programming. You do not have to use a third party library like the POSIX library or any other. So, using the primary component, which is the thread component in the library, you can launch a thread with a function object, or even with a lambda. So, you include that component, and suppose I have a function small f here, and you have a function object capital F here, and they do not do anything, they just kind of print a message. The overloaded operator just prints a message, and this is how you invoke the thread. So, you construct a thread T 1 with the parameter f, the function parameter, right. I am using the C++ style of initialization, because that is what you should be comfortable with. Similarly, it could thread T 2 could construct a functor object to initialize with, and as soon as that thread is constructed, as in here, it starts executing, right. Now, if you just run this program, copy paste and run this program, you will see that you are probably not seeing the outputs. It is not unlikely that you will see any result. The reason is, this thread gets started as soon as constructed, this thread gets started as soon as constructed, and then main comes to an end. So, main now I have created a thread, so it is done. So, the main will complete, but main function is the main thread in the process that you are running. So, once main completes, these threads are automatically terminated. So, they will not show you any effect. So, what we will have to do for an effective thread programming, we will have to tell the main thread that wait, these threads are still working, do not terminate right now, wait for them to finish. So, you say that by saying the thread variable dot join, T1 dot join. So, T1 dot join tells main that well, you wait till I finish. Similarly, T2 dot join says that. So, with this, now the both threads will have to complete before main can actually terminate, and therefore, you will see the result. This is now the interesting thing is, these are parallel, these are concurrent executions, they are happening at the same time, right. Even though T1 is constructed first and T2 is constructed next, and they start working as soon as they are constructed, it is not known in which order they will execute the corresponding cout. So, if you run it multiple times, in some cases you will find that the function f1 is executing first, and in some cases you will find the functor f is executing first. I tried 15 consecutive times, and out of that 10 times I got this and 5 times I got this, right. So, that is the indeterminism in terms of thread execution that will always be there. Now, this is fine as long as you are just printing messages, but obviously the function will need to have parameters. So, let us assume that our thread that the function or the functor that it is trying to execute, there is a parameter. So, the function has a parameter, let us say a vector, and what it does, it kind of prints the vector with a range for kind of construct, right. Similarly, the functor has a vector as a local variable, as a data member, and it is constructed with that, and the functor will also do that, it will print that vector. I have constructed a vector. So, now the question is, how do I tell the thread that not only this function, but I also need to give this parameter. So, for this you have a special template called bind. So, bind basically takes a function and one or more parameters of that function, puts them together into a function object, and then passes that to wherever it is required. So, it creates a functor instance from the function or the functor or the lambda and the parameters, right. So, the bind is successfully used in this case, in the first case, to take the function and the parameter to pass to the thread. So, now when the thread runs, it is invoking f with the parameter that myvec that we have passed. In the second case, since f is already a functor, we do not need a bind. All that I need to do is to construct an instance of f with the myvec, which I do here, and you can see the result that happens, right. Now, you will also see that if you run it multiple times, you will also see in some cases the functor runs first, on some cases the function runs first. It is indeterminable. Right. Now, so we have the thread execution, we have the input. So, now the question is how do you get the output? So, there are specific mechanisms to get output, though if as a plain task there is no notion of a return value. It is just an execution in the thread, right. So, it is not like a function which wherein you normally expect there will be a return value. No, this is a task. So, you just go and do that task, execute that function, execute that lambda and so on. But there are special mechanisms of that which we will discuss in the next module. But what you can always do is to get the output, you can pass some parameters as either a pointer parameter, or you can pass a reference parameter and get the output through that. So, let us say we pass the vector as an input and we pass a pointer to res, where in res we actually compute the sum of the vector elements. Similarly, here we introduce another data member in the functor and compute the add summation. So, what now happens is if I have to invoke the function, I have to bind the function f, the first parameter myvec, and a second parameter which is the result. The result is expected as a pointer to integer. So, I have to pass the address of that. So, this is very typical of how you call a function. You bind that, a functor is created and you invoke T1 with it. Similarly, a functor is directly created in capital F, and if you now run it, you will not only be able to see what the list of vector elements are, but after both of them have joined, that is finished, you can print the results and you can see that the results are appearing here. Right. So, we have more or less the basic tasks that a function needs to do or functor needs to do. We can do that using the thread, using concurrent executions. Let us take a little more elaborate look into what does std thread has. It is defined in the thread component as a thread. It represents a single thread of execution and allows multiple functions to execute concurrently in multiple different threads, right. So, return value is typically ignored, as I said, but if it terminates by throwing an exception, then std : terminate is called, which means that the entire program is terminated. So, if any of the threads throws an exception, then the entire program will be terminated. So, you will have to control that within that. So, there are mechanisms for communication of the return value, which we will see subsequently. But the most important thing is that a thread may not always have a function associated with it to basically execute. So, the thread may be in a state or a thread object rather, I mean not thread object may be in a state that it actually does not represent a thread of execution, right. So, this happens after a default construction, or you move the thread from the thread object to another thread object, you detach or you join when the task is completed, right. So, in this thread object is unique in terms of execution, that is no thread object can represent the same thread of execution. And interestingly, the thread objects are not copyable, they cannot be copy constructed or assigned, but they are movable. So, if you look at the basic primary structure of the thread class, you will see that there is a default constructor, there is a move constructor because it is move constructible. There is a parameterized constructor which is explicit. This is templatized, so that you can send, you can see there is a variadic template being used here, and it has a you can see that this is deleted, that is the copy construction is deleted. So, copy construction is not allowed. So, these are the basic properties. It has a destructor which which is executed at the end of its scope. There is an assignment operator which basically is a move assignment. So, if you move a thread from a thread object to another, then this thread object will not contain any thread. Now, we will see this through examples. So, I am just leaving with pointers to you. There are certain observer functions like joinable. Joinable is false before a thread starts execution or after it has joined. In between, while it is in execution, then it is joinable. Every thread has a unique ID which can get that. It has a native handle. You do not need not worry about these native handle and hardware concurrency right now, but the main thing is you can join, detach or swap thread objects. So, here is an example. So, let us look at this example. I have a function f1 and which basically repeats for 5 times, writing thread 1 is executing, right, and then it increments a variable, the variable that it has got as a parameter, it increments that variable every time. Okay. Now, then what it does is this long thing, what it means is something simple. This is std : this thread : sleep for. So, what you are saying that whichever thread executes this is this thread, and it says that this thread will now sleep, go to sleep for a certain amount of time, that is for this much time the thread will not do anything. So, that is what is available also in the thread component, and then you have to specify the time, and that is available in the library in the chrono component, where you say that chrono : millisecond, that is nanosecond and so on also, and how much. So, this ingest says that sleep for 10 millisecond. The second function also does a similar thing with thread 2. Then you have a class which has a member function bar, which does it for thread 3. Then there is another class buzz, which is got the function operator overloaded, it does the same thing and so on. Right. Now, if you execute them, so you will see that here I have constructed a thread without giving it a function. So, it has it does not have a ID, because it does not have any thread, right, it is just a thread object default constructed. In the second, we have given function f1 with a parameter n plus 1. So, this is another way of constructing the thread. Earlier we did bind and then pass the functor. Here we can directly pass that. We saw the explicit constructor with variadic templates. So, it does construct T2. Similarly, we construct T3 with another. We construct T4 by moving T3. So, the thread from T3 goes to T4. Therefore, you will see that between T3 and T4 the thread IDs are same. Then I have T5, which is from the member function. I have T6, which is based on a functor object, right. So, all these will come and then they are executing, and as they execute they keep on printing. Now, the difference is that as they execute, the order is not fixed. So, 4 threads are executing, right, but 4, 3, 2, 1, 4, 3, 2, 1. So, they are not necessarily, but later on if you just see that is the order, then you will see that it is 4, 2, 3, 1. So, this order is indeterminable, right. So, this is basically the typical thread execution. Just a little word about bind. Bind, as I said, takes a function or a function, any callable object and the parameters and put them together. And bind has a nice feature that it can put these parameters in the functor, and while putting them it can specify some of the parameters or leave some of the parameters for future. Right. And there is a particular namespace called placeholder, where these names, these are variable names, as you can see. Underscore is a valid beginning of a variable name, identifier name. So, underscore 1, 2, 3, etc. are defined. So, let us see, suppose you have a function with 3 parameters and you want a new function with 2 parameters, where the middle parameter here should be 4. So, you want this, you want, right. What you can do is, obviously you can write G and call this, that is a elaborate mechanism. But what you can do std bind f and then say underscore 1. Underscore 1 will mean the first parameter of G which will be called. Then the second parameter of f you keep as 4 fixed, and the third parameter you pass as underscore 2, which means the second parameter of G in future. So, now when we will call G23, it will actually mean a call F243. The first parameter comes here, and this order is arbitrary. You can put the first underscore 2 first, underscore 1. So, you can basically shuffle around the order of the parameters. You can make certain parameters default, you can use it. So, this bind basically makes a very generalized function pointer as a functor object, and it is very useful in passing parameters to STL algorithms. So, here below you have I have a simple example to show how it can be used as a callback. So, this is the callback type. You remember the function component. So, I say void float result. So, it means it will take a float, give me a void, that is the type, and I have a function that runs for a long time. So, what you do? You set another function, callback function, which basically will be called while this function has completed its task. So, callback float result, which says this is the result, right. And that now you wrap your long running function into an asynchronous function. You bind the callback with this particular function with a placeholder which is underscore 1, that is whatever you will give to callback as a parameter will go there, right. So, that is how result comes out here, right. Just try this out, this is good fun, and in the next 2 slides I have given different situations for bind, which you may just try out, right. This is not code to thread programming, but I thought that bind is so widely used in terms of creating function objects for threads that you should be more familiar with it. So, I have given a detailed example for you to try. Now, so that is the basics of what happens in terms of threads, but threads are a big boon in terms of it enhances performance, it allows you to keep on, when something is being done and the system is busy with that, you can still do something else in a different thread and so on, but they do not come without a price. So, there are different problems with threads. Now, the main is race condition and data race, right. So, these are talked about together. So, you might have thought that they are the same thing. They are related, but they are not the same thing, not at all. A race condition is more like a semantic error. A race condition is a situation where operations of multiple threads are kind of mixed up, interleaved, so that they are not producing a right result. That is a race condition. And a data race is when there is one single object, there are at least two threads which are accessing them, and at least one of them is trying to write. If multiple threads read a value, there is no problem, but if two or more threads try to write a value, at least one of them tries to write, others may be reading, then you have a data race. Often data race leads to race condition, but race condition may just happen by itself. So, let us take a race condition example. Suppose we want to do something very trivial, we want to work out this sum of square from 1 to 20. This by this formula, this is what should happen if 1 square plus 2 square, like that. And how we do that? We have a function square which squares the parameter and updates a global accumulator. Right? So, if I call square in a loop one after the other, then this sum will get computed. This is a sequential program. Right? Now, let us try to do this. Let us just for the sake of it assume that x into x, let it be a very heavy computation. Right? So, I want to do them concurrently. When 1 square is being done, 2 square should be done concurrently, 3 square should be done concurrently, and so on. X into x is not certainly heavy, but just using as a representative. So, what I will do, we will spawn 20 threads for 20 numbers. Each thread will do the square for as much time it takes and update the accumulator. So, at the end I should get that result. Now, if I do that, so I have the thread version, there is no changes here, but here what I do, I make a vector of threads and I push the 20 threads, each with a different value of I for the function square, and I am just using a raw function pointer here, and I just push that in the vector, create and push them. So, they are all in the vector. As soon as they are created, they start working, and then I run over that vector to see if they have joined. Right? So, this for loop will end when all of these threads have joined, and once that is done, my result is ready. Very simple program. So, now will it work? The question is, will it work? Right. So, you try it and it gives a result 2840, 2870 at its should. You keep on trying it, and well, you always get the result, and you are still thinking that, well, is it correct? Is it correct? Will this work? So, let us take two things. One is that, well, we had assumed that x into x is heavy, but we know that it is actually not heavy. So, let us make it heavier. So, what we can do? Instead of doing accumulator plus equal to x into x, let us compute x into x into some temporary. Let us sleep for a while and then add this temporary to the accumulator. This sleep effectively increases the perceived load or perceived computation time for x into x. Right? So, that way I just make the load heavier by introducing a delay. And then I say that it will not be the same for all numbers. 1 into 1 and 7 into 7 may not need the same amount of time. So, I just randomize, I put a random delay. So, what I do is I generate a random number between 0 to rand max and normalize it to 100. So, that I get a random number between 0 to 100, and then I use that in the millisecond. So, some occasion it will be 0 millisecond, 1 millisecond or 100 millisecond, and we try it again. Right? Now, so this is the total program. I am just so this is what you have done to put that random delay, right, which is what we have just discussed. Now, we say that okay, we again keep trying, it gives the correct result. I keep trying, I did this for 36 times, I got 2870, but on the 37th attempt suddenly I got a result 2845. The question is what is the problem? Is it a computer error or a false observation? So, I tried 100 more times, more than 100 times, but I always got to 870. So, I realized that before I can be convinced, I need to have some automated test for this. I cannot just keep on every time go to online GDB and run, getting mad. So, how can I do an automated test? It is very simple. I will just put this whole stuff of creating the vector of threads, spawning the 20 threads and joining of the threads within a scope, so that they are all localized, and put that in a do while loop. When have a trial count variable, every time it goes through this loop, this whole run has happened once and that trial count is incremented. And how do I terminate the loop? I terminate the loop by checking if the accumulator is 2870. If the accumulator is 2870, it is correct, right. So, then I will try again. If it is not, then I will exit. But that means that if the program is correct, it will be an infinite loop. Well, but then Murphy's law says that if anything can go wrong, it will. So, let us see what we find. So, with this is again the entire program, there is a random delay and this is the repeat. And since it might go on for a long time, what I do is after every 100 trials, I just print a message on the console that 100 trials done, 200 trials done, so that I know that the program is working, it is alive. And then I wait if a wrong result would come. Murphy was correct. I did this for 20 times, and you can see this is the actual data I collected. So, when I run this program for the first time, in the 56th trial it produces 2845. In the second trial, second run, in the first trial itself it produced 2806 and so on. In some cases it has taken 1502 runs to produce a wrong result, but in every case 20 cases it has eventually proved it. So, there is something wrong about this, and if you look at all these values, you will see that these values are less than 2870, all of them. So, what is going on? So, to understand, let us split into the simple square function as to what it is doing. So, what will the compiler do? Compiler has to multiply. So, the code written is necessarily x star x. Now, the compiler has to compute x star x into a temporary, has to read the accumulator into another temporary, and then add these two temporaries and put in the accumulator. This is a basic process. So, let us say I have two threads and they are independent. So, the order in which those instructions are executing can interleave in any way, but at any cycle only or at any point the instruction of only one thread can execute, because there is only one processor to execute. So, let us say if they are interleaved in this way, that it first does this in thread 2, then it does this in thread 1. So, in thread 2 T 1 is 4, in thread 1 T 1 is 1, then it does this. So, in thread 2 T 2 is 0, because accumulator initially is 0, then in thread 1 T 2 becomes 0, because accumulator is 0, then it updates the accumulators. So, in by thread 1 accumulator becomes 1, and then it does this, accumulator becomes 4, but it should have been 1 plus 4 5. Okay. So, you can see that interleaving only because that both these threads have in this process started with a value of the accumulator which is a non updated one, and both of them have updated after that, right, because of this interleaving, and that is the sole problem of having the incorrect result. And you can always see that it will always have a lower result than what is expected, and that is what we have been seeing, and this is exactly what is called the race condition, right. So, how to solve that, how to fix that? There are multiple solutions. So, I will just talk about two. One is solution by mutex. There is something like mutex that is defined, which is in the mutex component. So, you say mutex and give it a mutex variable name. Then you do a lock on the mutex. If you do a lock on the mutex, what it does, it is an atomic operation, and what it does, the first thread that comes here will get the lock and will be allowed to go and do the next instruction. But the second thread which comes to this point will not get the lock, because the lock has been given to one thread. So, it is like having a unique lock, unique key. So, till the thread which is having the lock has not released it, any other thread, all other threads will keep on waiting at this point. And when the thread which has the lock unlocks it, then one of these threads will get the lock again, and that will start proceeding, others will wait, right. So, this will make sure that at any point of time only one thread will be able to read and write the accumulator, because this is both read and write of the accumulator, right. And we put it in the solution very simply, only few lines are changed, include this, have a mutex and put these locks, and then try again, like our repeated trials with delay. If we do that, if we try again, and we will see, I waited up to 6,000 runs of this, and the program did not terminate. It is truly in an infinite loop. Another way of doing this is using what is known as atomic container. Atomic is a specific type of container, where whatever you put as an atomic container can be changed only by one thread, not by others, right. So, you can just say atomic, include this, say atomic, and things will get done. And this is so just these two inclusion of this, and instead of a global declaration you just say atomic int. So, it gives you an atomic integer, so that when it is trying to change the accumulator, which is atomic, no other thread will be able to read or write into that. This also solves the problem. Tried it 15,000 plus times and everything was okay, right. So, this is broadly the basic introduction to the thread programming and the race condition. We will talk more about these in the next module, but we have got a sense of how to create threads, how to run them, how to join, how to bind functions or functors to the thread, and how to solve a very simple problems of race condition using mutex or atomic. We will discuss more of these in the next module. Thank you very much for your attention.